Hello, everyone. This week we're going to be covering Chapter 5 in your registry review book, and it is titled Mammography Equipment. Okay, so first we're going to start with the X-ray imaging system. So know that within your X-ray imaging system, there are going to be three principal parts. Those parts include first the operating console. This is typically digital with touchscreen technology when you're talking about mammo machines. You also have your high voltage generator, which provides the high voltage needed for X-ray production. And then you're going to have your X-ray tube, which will actually create the photons that we utilize to image breast tissue. So incoming voltage to our machine. So line voltage from a wall outlet enters the X-ray circuit and is adjusted with a line voltage compensator. That line compensator is going to measure the incoming voltage from the power company through the outlet and adjusts it so that the voltage is precisely 220 voltage. We want a very precise voltage. We do not want it to fluctuate a lot. That can cause the circuit to short, things like that. Know that the incoming voltage can vary by as much as 5%. So the line voltage compensator is really important because it ensures the voltage going to the X-ray tube is always constant with no variations or fluctuations. Now the voltage then is going to go to the auto transformer, which is the first portion of your X-ray circuit. The auto transformer is going to have a kV meter, which allows the selection of various kVps across the output terminal. The output from the auto transformer is then connected to the primary coil of this step-up transformer, which is then going to move into our high voltage section of the circuit. X-ray production requires high voltage, and the step-up transformer or high voltage transformer helps convert that lower voltage into higher voltage, which is then sent to the X-ray tube. So then that brings us to alternating current versus direct current. So incoming voltage is going to be alternating, meaning that the waveform swings in a positive direction above the midline and then again into the negative portion of the waveform. Okay, so that's what is considered alternating. However, note that the X-ray tube can only operate on direct current. Okay, so the voltage is therefore converted using a system of rectifiers. So basically, we don't want this varying waveform. We only want a waveform that is on the positive aspect of this wave. So basically, what rectifiers do is they take these negative portions here and they move them onto the positive half cycle, which we'll talk about more here on the next slide. So rectification. Know that a rectifier is a solid state device that allows current flow in only one direction, thereby converting alternating current to direct current. The simplest kind of rectifier circuit is going to be the half-wave rectifier. Now, modern X-ray tubes cannot operate on half-wave rectification. In full-wave rectification, both cycles of the AC sine wave must be rectified using a bridge rectifier. So we're going to talk about what half-wave rectification is, but know that as technology has advanced, we have created different types of technology to enhance our incoming current. We have moved forward from half-wave rectification. Okay, so in a half-wave rectified direct current voltage, basically, if you picture our last example where the waveform comes on the positive half cycle, comes down on the negative, back on the positive. As you can see here, with negative half-wave rectification, all they have done is eliminate those negative half cycles. So now you are only having current flow during this positive half cycle, but you can see that there's a big gap. And the big gap is not ideal because those are pauses in current flow. So in order to mitigate that and to help current flow during those gaps of time, basically what they did is now they took that waveform and they took the negative half cycle and they flipped it upside down. So they used it as part of the positive half cycle. And what that did is it eliminated these timely gaps in current. It utilized the entire waveform. And now the distance between humps is going to be shorter, meaning that there's less time that it's going to take to go from zero to peak current. Okay. Then as they became more advanced with current, they developed what's called three-phase current. So now basically what they did is they added in two more waveforms, right? So now you have a total of six. Okay, so one, two, one, two, and then there's three different waveforms to equal six. And what that did is that eliminated once again the gaps in between each waveform. And by doing so, they kept the average potential higher and kept the gaps closer, meaning it didn't take as much time to get to peak voltage again. Then when they took the three-phase power and rectified it, once again, they took those waveforms that were going to be down below the middle line, which were negative. They flipped them up on their upside down, and now you have very minimal gaps in between each waveform. So now your incoming current is going to be near constant because those gaps have been eliminated. So that is the whole purpose of rectification, is we want to utilize those negative half cycles. We want to flip them up on the positive side so that we can get a more average high potential across our tube. So then that brings us to the timing circuit. So your timing circuit is used to shut off the high voltage to terminate the X-ray exposure after a selected exposure time. So when we want our machine to turn off, your timing circuit is what allows it to turn off and not keep irradiating the patient. Now, the timing circuit is going to consist of an electronic device whose action will make or break the high voltage across the X-ray tube. So it basically turns it on, turns it off. That's the whole purpose of the timing circuit. Then you have your filament circuit. Now, the filament circuit is going to be what's used to create thermionic emission at the cathode for X-ray production. The filament is located at the cathode end of the X-ray tube, and it is a coil of wire approximately 2 centimeters in diameter and 1 to 2 centimeters long. Now, note that in your filament, it's going to heat up and it's going to boil off electrons that are going to travel across the X-ray tube to your anode. Okay, so that is what the thermionic emission portion is. Now, connections from the autotransformer are going to provide voltage for the filament circuit. You then have a filament step-down transformer, which ensures that the voltage to the filament is low and the current is correspondingly high. So for your filament, you want a low voltage and a high current, because that current is what's going to cause sufficient thermionic emission, give us the tons of electrons that we need for X-ray production. Now, the step-down transformer is going to convert the high voltage from your high voltage side of the circuit and your low current, and it's going to convert them into low voltage and high current, okay, opposite of what was coming in. So once again, thermionic emission. So the high filament current is going to cause the filament to glow and to emit heat and electrons. That is the process of thermionic emission. Now that cloud of electrons will remain in the vicinity of the filament before they are accelerated to the anode when the high voltage is applied to the tube. Okay, so once that high voltage is applied to the tube, it is going to accelerate that thermionic emission cloud of electrons over to the anode for X-ray interaction. Now, thermionic emission is the term used to describe the boiling off of outer shell electrons of the filament atoms. So now we're going to get into your mammography tube. So this is an example of what your mammography tube looks like. It's typically made of Pyrex or metal, and it also has an electronic vacuum. It has 2 electrodes. The positive end of your mammography tube is going to be your anode with the target, and the negative end is going to be your cathode, which contains your filament. Then you have the housing of the tube. So you have your protective housing of the X-ray tube, which is going to be lead lined, and that helps to reduce the levels of leakage radiation. So if there's any photons that are traveling in a foreign direction within the tube, that lead is going to help absorb them before they actually exit the tube. This helps to protect the operator from the dangers associated with high voltage, and it also protects the tube against rough handling. Then you have your X-ray tube window or exit port. This is going to be the thin area of glass or metal enclosure. It's approximately 5 centimeters or 2 inches. And the window is what allows the X-ray beam to leave the tube. And it is also the light field that you see on your image receptor. Then that brings us to heat dissipation. So know that X-ray tubes get very, very hot. We are consistently creating tons of thermionic emissions, so we have to have a way to dissipate that constant heat production. So the X-ray tube uses a number of methods to dissipate the heat produced at the target. The tube is encased in an oil bath that serves as a thermal cushion to dissipate heat and an insulator to protect against electric shock. The tubes then have a cooling fan, and as the heated oil begins to expand, it will activate a micro switch to prevent an exposure if the expansion is too great. So it's kind of like a safety check-off valve that if the heated oil expands, if it gets too hot, that it might trigger another exposure. This micro switch will basically deactivate it. So here are some important modifications of mammography tubes. So of course, what makes them different than, say, X-ray machines? Well, we have compression devices, beam restriction devices, exposure factors such as KVP and mass are going to be different. Filtration is slightly different. Focal spot sizes, grid use, magnification methods is another big one, and then also target material. So the need for dedicated mammography imaging. Well, breast is all soft tissue. Typically within the breast tissue, you're going to have similar mass densities, which develops a need to maximize contrast. And we also need to be able to have the highest possible resolution because we are looking at very, very fine structures within the breast tissue. However, we do need to keep radiation doses as low as possible because we do know that the breast tissue is radiosensitive. So that is what all led to the development of dedicated mammography machines. So then that brings us to target material. So in mammography, the typical target material is going to be molybdenum. And this is because the prominent X-rays are characteristic X-rays produced after a photoelectric interaction. And the X-ray range for breast tissue is going to be anywhere from 17 to 24 keV. You can also use rhodium targets. The atomic number is going to be slightly higher than molybdenum, and it has a K characteristic X-ray of 2 to 3 keV higher than molybdenum. Okay, rhodium is helpful when trying to better penetrate dense breast tissue. Then for digital mammography tubes, we have tungsten targets. Now know that tungsten are going to emit harder spectrum rays, meaning a more homogeneous beam, meaning that the energy levels of your beam are not going to vary. If you set 20 kVp, your beam should have a majority of 20 kVp X-rays. Now, with tungsten targets, they do offer a wider dynamic range that can be utilized for digital. Note that single tracks are more reliable and less expensive. Single track tungsten tubes support 2 to 3 times the max anode load versus a dual track. Okay. So what is the need for filtration? So know that filtration is going to be defined by the half value layer of your machine. And half value layer is simply how many millimeters of aluminum does it take to reduce your X-ray exposure by half. Okay, so the higher the half value layer, the higher the filtration. Okay, now note that with filtration, it's going to result in fewer X-ray photons below the preferred mammographic energy range. It also reduces exposure time, which eliminates potential patient motion. Okay, so anytime you're using a filter, whether it be in mammography or even X-ray, there is a fine line between when filtration is helpful and when it can be used in excess and actually does us a disservice. So types of filtration. Inherent filtration, meaning within the tube, you're going to have your oil bath, which surrounds your X-ray tube. You're going to have the glass or metal window of your X-ray tube that is going to absorb low energy photons. You also have your mirror assembly, and then of course the compression plate. Examples of added filtration are going to be rhodium, silver, or aluminum equivalent material, and typically those are used to determine what the half value layer is. And then also molybdenum can be an example of added filtration. So with molybdenum and rhodium targets, the filtration is generally the same element as the tube target. So for tungsten tubes, you're going to have tungsten targets, okay? For fatty breasts, you could have a rhodium target. For dense or large breasts, you could have silver, okay? For, that should say, tungsten tubes, that should say silver on this second part. I apologize. So the fatty breast is going to be molybdenum, whereas aluminum is going to be used in digital tomosynthesis units and photon counting imaging systems. So minimizing inherent filtration. So starting with the glass window of the tube. It's typically made of beryllium or borosilicate glass, and it does not attenuate low energy photons needed for mammography imaging, which is really important because when we are imaging breast tissue, we don't need super high energy photons. So you do not want to use a type of glass window that is going to absorb all those very low energy photons that we need. So there's a fine line between absorbing too many or not absorbing enough. Now, the common target filtration combinations are as follows. So a molybdenum target with a 0.03 molybdenum filtration. For machines with a rhodium target, they can have a 0.025 millimeter rhodium filtration. It's common to see molybdenum and tungsten targets with both molybdenum and rhodium filtration. You can have molybdenum and rhodium targets with molybdenum and rhodium filtration. And then you can lastly have a tungsten target with rhodium or silver filtration. Then that brings us to the line focus principle. So the line focus principle allows a large area of the focal spot to heat while keeping the effective focal spot small. Now note that with line focus principle, decreasing target angle is going to decrease the effective focal spot size. So basically, in this example here, you have your electrons from the cathode that are traveling across your X-ray tube to interact with your target angle. Now, the area that they interact with on that target angle is going to be considered your actual focal spot size. Okay, it is that area in which these electrons are going to interact. Now, after interaction, when they get emitted out of your X-ray tube, that is what you call your effective focal spot size. And when you decrease this target angle, you are going to decrease your effective focal spot size. Okay, now note that with a small focal spot, that's going to give you greater detail. So a small effective focal spot is ideal. So then that brings us to half field geometry. So the central axis of the beam is parallel to the chest wall. A 24 by 30 centimeter field of view typically requires a tube tilt and anode angle of anywhere from 20 to 24 degrees. Now, a 0-degree anode tilt would require that the tube be tilted anywhere from positive or negative 24 degrees. Now, the typical 16-degree anode angle is accompanied by a 6-degree tube tilt. And what this means is that because your chest wall runs parallel to the central axis of this beam, we have to tilt our anode so that we can utilize the high energy photons on the cathode side, because this is the denser part of the breast tissue against the chest wall. And then you use the lower energy photons that are going to be on your anode side for the nipple end of the breast. Okay, same thing that we do in X-ray with utilizing the fat cat method, if you guys have ever heard of that, where you put the thicker part of a body part underneath the cathode. So for example, if you were imaging a femur, you would put the knee end of the femur underneath your anode, and you would put the thicker part underneath your cathode. Well, same thing in mammography, except now we're putting the chest wall end underneath the cathode and the nipple end of the breast underneath the anode. So then that brings us to focal spot size. So know that 0.4 millimeters or smaller is typically used for routine work. The most commonly used is going to be 0.3 millimeters. Now, when dealing with magnification, a 0.15 millimeter or smaller can be used. However, the most common focal spot size in magnification is going to be 0.1 millimeters. So then going back to our anode heel effect, we know that the anode heel effect is going to help reduce variation of intensity due to the heel effect, meaning that anytime you have an X-ray beam, your X-ray beam is always going to have a lower energy on the anode side. And that is because this target material is going to absorb part of your X-ray beam. So what gets emitted ends up being a little bit smaller energy or decreased energy as compared to the cathode side. So the tube is orientated to place the nipple at the anode to reduce the effective anode heel effect and maximize homogeneous density across the breast. So KVP and digital imaging. So image acquisition and display are separated. The user can alternate or can alter the image contrast after the exposure. The controlling factor of contrast is going to include KVP, the processing software with your machine, and of course, digital algorithms. Now, the wide latitude in digital allows visualization of the skin and penetration of dense breast tissue. Then that brings us to exposure time, MA, and mass. So MA and exposure time are combined to create mass. Now, mass determines the number or quantity of X-rays being produced. Now, we note that we always try to use as high of KVP as possible and as low as mass. Mass must be kept short to reduce motion blur. We also know that mass is going to significantly affect patient dose. So if you're using high mass techniques, you're going to get a higher patient dose. And then also, MA does not affect image brightness. Then that brings us to the compression plate. So your compression plate must be made of a low attenuation material so that it does not absorb a hefty amount of your photons. It must have a rounded posterior edge to help with patient comfort. It needs to have a straight chest wall edge, meaning the side of the paddle that is going to brush up against the chest wall needs to be straight. And the device should rest flat or at least parallel with the detector. So digital AEC detectors, just like an X-ray. So AEC is used in all modern mammography units, and that's to control the actual exposure, therefore ensuring a uniform density of the final image. Now, with automatic exposure control on dedicated mammography machines, the chance of repeats and additional radiation exposure dose to the patient will be significantly reduced. Now, note that in digital, because the detector covers the entire field size, the system is easily able to respond to a very small or a very large breast. So exposure modes, we have manual, where this is going to be when the operator selects all parameters. You have your auto time, which is when the system is going to select your mass and the operator selects filter and KVP. Then you have auto KV systems, which are going to select the KV in the mass and the operator selects the filter. And then lastly, you have an auto filter system, which is going to be when the system selects the filter, the KVP, and the mass. So whenever you're dealing with AEC, we have backup timers, and backup timers are needed to avoid gross overexposure. Now, note that with mammography machines, the maximum backup time required is going to be 600 mass for grid techniques and 300 for non-grid work. Now, you want to avoid the backup timer by using higher KVP, not higher mass, because therefore your patient radiation dose will be significantly higher. Now, the backup timer will reach when imaging implants using AEC. So typically you'll use a manual technique if you're imaging patients with breast implants, because those implants are so dense that the backup time will automatically max out when placed over the AEC chamber. All right, so next is grids. So we do use grids in mammography, and grids help to improve overall contrast. They help to decrease scattered radiation, which can ultimately create more noise on our radiographs. and they result in more radiation dose to the patient. So they're always used in routine imaging. Okay, so your screening mammos, diagnostic mammos. However, they're never used in magnification mammography. So, what are the characteristics of a grid? So, you can have a linear or focused grid. In a grid ratio, a normal one for mammography is anywhere from a 3:1 to a 5:1, and it's focused to the SID used. Now, a grid frequency of 30 to 50 lines per centimeters is normal. And then also the grid interspace material used is either carbon or wood. Now, note that the grid frequency is going to be the number of grid strips per inch or per centimeter. And your grid ratio is going to be the height of those strips over the diameter. Then that brings us to a high transmission cellular or HTC grid. Now, these have a characteristics of a crossed grid. They help reduce scatter in two directions rather than one. And for the lead strips, they use copper. And then for the inner space material, instead of carbon or wood, they use air. And they result in less radiation to the patient. So, for example, in a normal grid, you would just have your strips, right? And then your inner space material in between. Well, with a crossed grid, you're basically creating like a picnic basket. So now we're having grid or lines go horizontally and vertically, which helps to reduce scatter in both directions. Then that brings us to beam restricting devices. So this is going to be our collimation. So despite the benefits of collimation, in mammography, the exposure field is restricted to the size of the imaging plate. The entire image plate and not just the area of the breast is exposed, which is why on mammograms for a medium-sized breast, anterior to that breast tissue, you'll see black, and that's the rest of that image plate being exposed. Now, this is done to prevent extraneous light from compromising the perception of the fine detail when the radiograph is viewed. However, under MQSA standards, the collimation should not extend beyond any edge of the image plate by more than 1% of the SID, and that is calibrated and measured when installing a machine. So SID and OID. In mammography, the recommended SID is going to be anywhere from 50 to 80 centimeters. OID is as small as possible, except in magnification. So when you're doing standard mammography, we want to keep OID to a minimum. However, we use OID to our advantage when completing magnification views. So magnification, we use this all the time in mammography, and it's used to assess small lesions or microcalcifications. Generally, magnification will reduce the resolution of the image because of geometric unsharpness. So to compensate for the lost resolution, a very small focal spot is used. Now, the standard is going to be 1.5 and 1.8 times, but some machines will offer two magnification factors with one as high as 2 times. So to magnify the breast, the OID is increased by placing the breast on a raised platform or detector holder. Remember that grids are not going to be used in magnification radiography because the large OID is going to serve as an air gap to reduce the scatter to the detector and increase the overall detail. So focal spots for magnification. For routine work, you can use a 0.4 millimeter or smaller. The most common is going to be the 0.3. For magnification views, you're going to use a 0.15 millimeter or smaller, but the most common focal spot size is going to be a 0.1 millimeter. This is an example of a magnification stand. So the patient's breast would be placed on top of this platform, which creates probably about 12 inches of OID. You use a smaller magnification paddle to cone down to the specific area of the breast of interest, and then basically you'll get an image that is the size of this little paddle. So in digital imaging, the acquisition, display, and storage are all separate functions which can be independently optimized. Now, note that wide exposure latitude and dynamic range play a role in digital imaging. a linear response to the intensity of X-ray exposure, and also the ability to optimize contrast. Now, note that latitude is going to be the range of exposures over which X-rays will respond to optical densities, is considered your latitude. So these are examples of digital images of a dense versus a fatty breast. So of course, in the dense breast, we can see great detail. You can differentiate fibroglandular tissue from the more fatty tissue. You can see the skin line here, nice and calcified like normal, or kind of white in appearance is the skin line. On this fatty breast, you can see the majority of fatty breast tissue with scattered fibroglandular patches within. So then that brings us to monitors within our imaging system. So monitors can be liquid crystal display, LCD, and the organic light emitting diode display, OLED, are now more common. Now, when viewing images directly on a monitor, the ambient light should be strictly controlled, meaning that you don't want, surgery lights on when you're trying to look at the monitor. Ideal lighting, ambient light, so that you can actually see what you're looking at. Older technology monitors included a cathode ray tube, or a CRT. So comparing the CRT versus the LCD. So a cathode ray tube had more luminance and better color reproduction. It was considered to be more durable and a faster refresh rate. However, the LCD had less energy consumption, produced less screen glare, and had better resolution. And it was also lighter, significantly lighter. So it's just like, back in the olden days when you had the big box TVs where the back of them would be, 2-3 feet deep, whereas now the TVs are, pencil thin. So the digital image, your digital image is going to be formed as a two-dimensional or 2D matrix of picture elements, which are called pixels. Now, the matrix is going to be a box of cells with numeric values arranged in rows and columns. And then each cell corresponds to a specific location in the image. Then that brings us to your acquisition workstation. So after the exposure, a digital image will pop up almost immediately at the technologist workstation monitor. This workstation is also called the acquisition workstation. Those workstations are typically low resolution and have an image resolution of 2 or 3 megapixels. These images on these monitors are sometimes referred to as the soft copy images because the image data can be manipulated to attenuate or suppress various features of the image. Okay, so same thing as in X-ray, this is where our images pop up, that we can make notations, we can window level. That is all on the technologist acquisition workstation. So changes that can be applied at that workstation. So first, we can adjust the image contrast and brightness, and that is called window and leveling of the image. Now, window width is going to control contrast, whereas window level is going to control brightness. Now, the brightness value of adjacent pixels in the image can be brought closer together in a process called smoothing. All or parts of the image can also be digitally magnified with the zoom feature rotated, flipped, or inverted. Now, the brightness of the edges of all structures can be enhanced in a process called edge enhancement. This process increases the visibility of the edges of structures. Now, note that the background of the anatomy can be removed, which will allow visualization of other relevant anatomy. Now, in mammography, that does not happen all that frequently. Additionally, the image can be reversed. So in a reversal to a positive image, the dark and light pixel values in the image are reversed, and dense structures would be visualized as black. So you're inverting the image to make those contrast colors opposite of what they were. Lastly, in a process called annotation, text, a ruler, and other markings can be added to the image. Then you have your review workstation. So this is going to be where your radiologist sits. Okay. They can also be called your interpretation monitors. So these are going to be used by the radiologist for interpretation, and all diagnostic interpretation must be conducted on monitors certified by a physicist. So these monitors are going to have their own set of QA procedures, and they do have to be certified by a physicist to ensure that those doctors can see the fine details within the mammogram as outlined by the MQSA. So monitor QC, those checks are going to include a check of the luminance to monitor the brightness of the monitor. You also do a check of uniformity to check that the brightness over the surface of the entire monitor is the same. You do a check of the contrast to monitor the ability of the monitor to display the full range of densities produced by the digital system. So can you see all shades of gray that you would anticipate? And then also a pattern test to detect bad pixel, spatial resolution, contrast resolution, and viewing angle cutoff. Many monitor manufacturers will provide a program or list of tests that must be conducted daily, monthly, or yearly. Then that brings us to print and storage options of images. So the first one being printed film. These are going to be laser printed images. They have lower resolution and are sometimes not of interpretation quality. You also have digital linear tapes or DLTs. These are going to be magnetic tapes used in a cartridge tape unit. The image is encoded on the tapes based on the principle of electromagnetic induction. So similar to a VCR tape. Then you also have optical discs, which are going to be your CD and your CD-ROMs. These are going to be your most common, okay, in digital imaging. They can be stacked in multi-disc formats in drives called jukeboxes that can handle up to 100 discs. Optical discs are also called laser discs, and they use laser technology to read and write to the disc. And then lastly, you have your redundant array of independent disks, or your RAID. And a RAID is actually a system of 2 or more disk drives within a single cabinet that collectively act as a single storage system. Now, the advantage of this technology is that if one disk drive is defective, the others can take its place. So they fill in for the other. So this is an example, of course, of a CD and then a linear tape, which looks just like a VCR tape. Then that brings us to Lucy and Lucy-less compression, which sounds silly, but it's very important. This is something that will be on your mammography registry. So note that for mammography, we use Lucy-less compression. So know that images can be archived on a short-term basis via local storage on the hard drive of a workstation. They can also be stored via the RAID. They can be stored long-term by means of optical discs or DLTs. However, other radiography images can be compressed, thereby reducing the required data storage capacity by storing data in encoded form. And this allows for a more efficient use of storage space. So in information technology, Lucy compression reduces a file by permanently eliminating certain information, especially redundant information. So for example, JPG compression is going to analyze the images in blocks of 8 by 8 pixels in size, and then selectively reduces the detail within each of those blocks. So they're consolidating the amount of data. When the file is uncompressed, only a part of the original information is still there. Now, these techniques are used to reduce data size for storage, handling, and transmitting content. However, with lossless compression, this is going to be a class of data compression algorithms that allow the original data to be perfectly reconstructed from the compressed data. So lossless compression is used in mammography because it is vital that the original and the decompressed data be identical. The image is broken into smaller blocks of data at origination and put back together at the destination. Now, with lossless compression, every single bit of data that was originally in the file remains after the file is uncompressed. So it's a way for us to consolidate our mammography films without losing any of that true original data. So example of storage options, a single 18 centimeter by 24 centimeter image can need 16 megabytes of storage space, whereas a 24 centimeter by 29 centimeter image can need 28 megabytes of storage space. Now, a DLT magnetic tape is going to only hold 35 gigabytes. One optical disc can hold 3,000 CR images or 250 megabytes of data. A single optical disc can hold 4 gigs, and a dual disc can hold 8 gigs. And then note that the multiple platter optical jukebox, which is a series of optical discs, can hold up to 5 to 10 terabytes. So that's just to show you in perspective what each of these medias can store. Then that brings us to PACS, or the Picture Archiving and Communication System. So this is a complete integrated system that offers the conveniences viewing images from multiple modalities such as mammography, ultrasound, MRI, all at one workstation. PACS also eliminates the need to manually file, retrieve, or transport images. So, for example, in the olden days, we used to have mammography film rooms where every time a patient would get a mammogram, you would have to print out their films, put them in their folder, and you'd have to keep them for the lifetime of that patient going to that facility. Well, with the integration of PACS, we were able to digitize those films, and now you don't need all that storage space. It's all virtual. So the PACS image storage and retrieval system uses the DICOM, which is Digital Imaging and Communication in Medicine Standard, which we're going to talk about on the next slide. This allows the option of scanning non-image data, such as patient documents and results, into the PACS system for later retrieval. So some of the advantages of PACS. So once an image has been acquired onto the PACS system, it cannot be lost, stolen, or misfiled. PACS, once it is fully integrated, can allow the placement of numerous PACS terminals throughout a facility. This allows simultaneous multi-location viewing of the same image by different individuals as needed. And the PACS database ensures that all images are automatically grouped with the correct examination, are chronologically ordered and correctly orientated and correctly labeled. PACS allows the easy retrieval of patient images using a variety of criteria, such as name, hospital number, date, or referring clinician. PACS also allows the user to manipulate the post-processing part of an image. So you can pull up an image on PACS, you can window level it, invert it without actually changing the original data. And then after the exposure, all the patient's images can be sent immediately to the PACS system and will be immediately available for viewing. So what are some of the disadvantages of PACS? Well, the biggest is going to be installation expense. It's a very expensive system, and it takes a little bit of time to integrate. The PACS systems must also be protected against system failure. So all facilities using PACS should have a contingency plan in case of total failure of the system. And in addition, the system should be equipped with automatic data backups to avoid data loss. PACS also offers an option called prefetching, and this is basically previous images on a patient to allow immediate comparison, meaning that if you shoot a mammogram today, PACS can prefetch their last known mammogram so that when the doctor pulls up their initial study from today, they will see last year's mammogram for comparison. Okay, which is very, very common in mammography. They always use comparison. So this prefetching tool is very, very useful. Then that brings us to DICOM, HIS, RIS, EMR, and HL7. So DICOM, once again, stands for Digital Imaging and Communications in Medicine, and it's one of the most widely deployed healthcare messaging standards in the world. It is used for handling, storing, printing, and transmitting information in medical imaging. This system allows communication between different medical imaging devices, such as scanners, printers, servers, workstations, network hardware, and PACS from multiple manufacturers. Each device comes with a DICOM conformance statement, which clearly state which DICOM classes they support. whereas the HIS is also known as the Hospital Information System. This system is going to focus mainly on the administrational needs of the hospital or health facility. It can be a comprehensive integrated information system, and it's designed to manage all the aspects of a hospital's operation, so medical, administrative, financial, and legal issues, and the corresponding processing of those services. And then the hospital system would include patients' medical records, initial diagnosis, treatments, and all diagnostic tests performed. Then you have the RIS, or the Radiology Information System. So this is the digital information storage and retrieval system used in imaging departments. Now, the major functions of the RIS can include patient scheduling, resource management, patient registration, examination performance tracking, examination interpretation, results distribution, image tracking, and procedure billing. And then lastly, we have the electronic medical record. So an electronic health record or electronic medical record refers to the digital collection of patient health information data. These records can be shared through network connected systems within a facility or with other facilities. So the electronic health record may include demographics, medical history, medication and allergies, immunization records, lab and diagnostic test results, radiology images, vital signs, personal statistics like age and weight, and also billing information and points of contact. The medical record can give patients, physicians, and other healthcare providers, employers, and payers or insurers access to a patient's medical records across facilities. It can also reduce the risk of data replication and is more likely to be up to date. It also decreases the risk of lost paperwork and allows searchable digital information in a fast and easy way. It's also more effective when extracting medical data for the examination of possible trends and long-term changes in a patient's status. And then we have health level 7 or HL7. So ideally, all the systems, DICOM, HIS, RIS, and EMR should communicate with each other. Now, the Health Level 7 International Organization is a not-for-profit organization that developed a system to standardize communication to allow the speedy management, delivery, and evaluation of health services. They are able to fill the gap and allow the different computer systems within a hospital or healthcare setting to communicate with each other. And with this system in place, clinical and administrative data between software applications can be transferred, shared, and retrieved. These include billing records, patient demographics, medical records, or appointment schedules. Then you have your WAN and LAN. So WAN is going to be a wide area network. This is going to be a computer network that covers a large geographical area and generally involves major telecommunication or internet links. Whereas a LAN is going to be a local area network, which is a limited computer network. So a LAN network would interconnect computers to a server within a small geographical area, such as within a school or a hospital. Computers and other mobile devices using a LAN connection can share resources such as a printer or network storage. Teleradiography. So this is very, very common. This is moving into radiology quite abundantly. So transmitting digital mammography signals involve the transmission of huge data files, typically as much as 32 megabytes in size for a single projection. And the transmission must often occur without timeout to avoid compromising the signal. Now, a 4-series mammogram could therefore involve transmitting a 125 megabyte file. If the patient had prior studies, the total could easily exceed 0.5 gigabytes per patient just for a basic screening study. In comparison, a typical MRI consisting of over 100 images will need about 6.5 megabytes. And then CAD can also add approximately 0.2 gigabytes to the data load. And CAD stands for Computer-Aided Detection, which we're going to talk about next. So PACS and teleradiography. Note that PACS is going to allow for modality comparison, modality integration, and prior image comparison, whereas teleradiography is going to allow for virtual consultations, internet access to images via the telephone, cable, or satellite. Then that brings us to CAD, or computer aided detection. So this is going to combine digital technology with computers to pre-read the mammograms. They basically screen them before the doctors even look. So the computer displays suspicious areas and normal structures are de-emphasized. Now, CAD technology works with both digital mammography and analog mammography. Its high sensitivity will increase the false positive rate, and high specificity will reduce the number of false positives. So the doctor still has to read the mammogram, but it can certainly help detect areas that maybe weren't visible to the human eye initially, or it can at least guide the doctor to a section of the breast that may have something abnormal. So image quality in digital and computed mammography. So the image acquisition, the image display, and the storage of the images are separate functions in digital mammography. This means that after the image has been acquired, these functions can be modified based on the capabilities of the digital software. So, brightness. In digital mammography, the term density has been replaced by the term image brightness. And the brightness of the image is controlled not by the mass only, as in analog imaging, but also by the processing software with which include predetermined digital algorithms. Now, the user can alter the brightness of the digital image after the exposure via post processing. Whereas image contrast in digital imaging is not controlled only by the KV, but also by the processing software, and the user can modify the image contrast after the exposure. So basically, brightness and contrast can be affected by post-processing algorithms. Then that brings us to resolution. So resolution is the ability to image two separate objects and visually distinguish one from the other. Now, resolution is directly related to focal spot size. As the focal spot size increases, resolution decreases. Resolution is affected by the focal spot size, the overall SID, and the OID. Whereas spatial resolution is going to be the ability to image small objects that have a high subject contrast. So, for example, breast microcalcifications. They're very, very small, but they are also very bright, meaning that they are white on a mammogram. So spatial resolution in digital imaging is also controlled by the acquisition of the image, including the pixel size and display matrix and the capabilities of the monitor. Now, the smaller the pixel size, the better the spatial resolution of the image. In general, digital systems have a lower spatial resolution than screen film analog systems, and it is therefore important to control either other geometric sources or motion. No digital system has even close to the resolution of 11 line pairs per millimeter, which is the minimum required for screen film systems. So contrast resolution is going to be the ability to distinguish anatomical structures of similar subject contrast. So you're comparing shades of gray, and how well can you distinguish between those shades of gray? The more pixels there are, the greater the pixel density, which is the number of pixels in a unit area. The greater the pixel density, the higher the image resolution. Spatial and image resolution. Resolution is measured in line pairs per millimeter or inches. So the smaller the pixels, the greater the spatial resolution. The greater the number of pixels, the greater the image resolution. So when we're talking about detail, less precise terms used would be detail, recorded detail, visibility of detail. And it's the ability to visualize recorded detail when image contrast and optical density are optimized. Whereas more precise terms used today would be spatial resolution is going to pertain to detail. Contrast resolution is going to be attributed to recorded detail, and contrast resolution can also be looked at as visibility of detail. And then lastly, that brings us to focal spot blur. So this is caused because the focal spot is a rectangular area on the target and not a point. And the size can vary anywhere from 0.1 to 1.5 millimeters. Now, focal spot blur is represented by a blurred region on the radiograph, and it can be reduced by a small focal spot size using a larger SID and a shorter OID. Motion. So we always know that in X-ray, mammo, any imaging modality, motion is always of concern. So voluntary motion is under the direct control of the patient and is best reduced through patient communication. So communication should be given to the patient before the start of the mammographic examination to ensure patient cooperation in reducing that motion. So for example, can you hold your breath? Involuntary motion is not under the conscious control of the patient and is best reduced by decreasing exposure time and using immobilization techniques. Involuntary motion is also controlled in mammography imaging by good compression, which then reduces breast thickness, allowing for shorter exposure times. Then you have noise or quantum noise. So, noise refers to the random disturbance that obscures or reduces image clarity and will appear as a grainy or mottled image, sometimes referred to as snow. In imaging, noise is controlled by the milliamperage, defined as the actual number of photons striking the detector. So we know that mass is quantity. Now, low exposure factors, kV and mass, will produce few photons, therefore less signal and more noise. Higher exposure factors will produce more signal and less noise. However, more scattered radiation will be produced. And a high signal to noise ratio, or SNR, is the best and can be controlled by the initial MA and the use of grids to reduce scattered radiation. So that brings us to resolution and sharpness. So all images will have less resolution and sharpness than the object itself. Changes in your SID, your OID, and the size of your collimated field will not affect focal spot size. In mammography, in order to produce the sharpest possible image detail, the smallest possible focal spot size is coupled with the longest SID and the smallest possible OID. So we want a small focal spot so we get great detail. We want a longer SID, and we want the smallest possible OID. Okay, and that is all I have for you for Chapter 5.